Good evening, everyone.
It is.
Wow, this is a great crew. I didn't expect this on Valentine's Day. Pretty amazing.
Well, we love you.
Yeah, I love you all too, really.
You have your red shirt on.
And on purpose, and I'm surprised. Not a lot of red out there. So welcome to the 917th meeting of the Amateur Telescope Makers of Boston. Really excited about tonight. We've got a great set of slides for our business meeting. And then Camille is here to give us a great presentation on black holes. So without any further ado, let's get on with the business meeting.
You remind me of Jimmy Kimmel in that opening. You should tell a joke or two.
He is a joke.
That is a fun story. Did I say anything about the peanut gallery?
Yeah.
So
I will separate these guys.
Seconded.
all in favor? If just the elections could go that well. So we have a packed agenda, so we'll get going. Right? And is Eileen available?
She's coming.
She's coming. All right.
She just came because of Valentine's Day.
All right. Oh, but first I wanted to have a moment of silence. As most people are aware, the Opportunity rover has not woken up, so the mission has officially ended for the Opportunity rover and for the whole program. So I don't mean to make light of a moment of silence, but a lot of people, a lot of energy, resources went into this amazing program. So I think it's important for people to really think about, what humans can do to really drive science and really reach for the stars. And so just some cool things. The mission plan, it was really meant to last for about 90 days. And it almost made it to 15 years, which is pretty amazing. And that goes to the engineering involved in the making of that instrument. And then, over time, it sent over 200,000 images back, not to mention all the other information that was sent back. And it traveled over 28 miles. And it was originally designed to only span 1,000 meters. So absolutely amazing. So, and some of the science, there's a great picture on the website, and I'm using Astronomy magazine here today. They had the first extraplanetary meteorite right next to the rover as it opened up. It was right there in the blast shield. And then some of the biggest things that some people really think are significant is that the presence of water was really made known through this mission. So not a big surprise to me, and I guess it is to a lot of planetary scientists, but it was a good run, I think. And, it just goes a lot to the engineering and the passion that people have for science and astronomy in general. Okay, we have the observing committee, Len and Bruce.
I got an email from Jim Mulaney, who used to write for Sky and Telescope many years ago, and he sent me a whole bunch of astronomy sayings, so I'm going to start throwing them up on the observing committee report. And I like this one. I would rather freeze and fight off mosquitoes than play astronomy on the computer. It's been kind of a tough year. We'll go ahead to the next slide. And a couple of events coming up. On the 18th in the morning, Venus and Saturn will be pairing up in the morning sky. On the 26th, Mercury will be at its greatest evening elongation. This is actually a fairly favorable one. You still need a fairly low horizon, but it's going to be well seen this particular time. And you look low in the west about 40 minutes after sunset. On the 27th, February 27th, Jupiter and a waning crescent moon will pair up. I bring these out because this is a good time for anybody that's never seen the planets. It's always good when the moon is kind of a marker. You can find the moon, then that bright star near it is that particular planet. And I wish when I was a kid at school, my teachers had brought that up. I always wanted to know, where is Mars tonight, where's Jupiter? And if you could find the moon, you could find these objects. And then on March 1st, Saturn and the waning crescent moon will be pairing up, so they'll be near each other. And the bad news, on March 10th, daylight saving time begins. The clock spring ahead an hour. I was driving in, it was about 6 o'clock, and there's still a little bit of light. At that particular point, once we change the clocks, it's not going to start to get reasonably dark till after 7:30, 8 o'clock, and that's when we have trouble with these star parties for kids. So sometimes you want to get a star party in for the kids, try to get them in before the clock changes. After that, and of course the days are getting longer, we start to lose these opportunities to do star parties, especially for younger kids. Go to the next slide. The Observers Challenge, and by the way, yes, Bruce.
Before you move on, interesting opportunity on the 27th. There will be an ISS transit of the moon visible to most of the Boston area. Do a search on ISS transit and you'll be able to, the first site that pops up is the one that'll give you the information. I'm hoping to film that in 4K at about 3,000 millimeters from New England SciTech.
Well, you know, Bruce, I will forget everything you said the minute I sit back down. So could you send something out to ATMoB announce just to remind everybody? I mean, I did that yesterday for you all. I told you about that conjunction of Mars and Uranus, about the comet, and then the minute I sent that thing out, the clouds came in and filled up the sky. It's beautiful right now, by the way. Crystal clear skies.
3:22 p.m.
And it's going to stay that way until Tom hits the gavel at the end of this meeting and the clouds will move
during the day.
Okay, Observers Challenge. I just heard from Roger Iverson they're going to change the name of this. This used to be the LVAS Observers Challenge, but that club is kind of, not many of them in that club are doing it anymore. It's now the ATMoB Observers Challenge. Someone's doing it. But anyway, this is the one this time around. It's the Monkey Head Nebula, and Mario took a nice picture of it, which I didn't put up here, and he's not happy with me, so from now on, he's going to send it to me right away, because I'd rather somebody in the club use ours than use something I stole off the internet. Has anybody seen it, by the way?
The internet?
Is that because I work for Astronomy Magazine? Who's seen it before? It's like, what was your impression of it?
It was just no defined shape. Just you could see there was something fuzzy there. I was watching with my 8-inch, Smithcast. There was something there. It got a little bit more obvious with a filter, nebula filter. But it kind of looked fairly round. You know,
Now,
not elongated.
In your
really.
left-hand image, it says 2174, and the title says 2174.
all right, there is a reason. I wrote that in the article. It should be in the newsletter. There's a lot of confusion about that because there's a cluster there that's mixed in with that. So some of the maps I have, in fact, I think the Sky Atlas 2000 has it as 2174/2175. And there was a lot of confusion. I think it was Stephen O'Meara who said he thinks it is 2175. But again, put them both together. There apparently is a cluster involved with it. Did you notice any cluster around that area, any cluster stars in
I
there?
really couldn't tell. I knew there was supposed to be a cluster, and there were just stars kind of evenly distributed
Rich, did you
there
see it?
and all around it. It was not an obvious cluster to me.
I use my 10-inch scope from Framingham when the skies are, the NELM is about 4.8 on a good night. The two stars that mark sort of the center of the nebulosity were, of course, most nebulosity I saw was around those stars. And I looked at that little trio of stars to the bottom. See that right there is kind of like the extent of the nebulosity. You're right, filters helped a little bit, but it's diffuse, it's really big. So try to use the lowest power you can, maybe a 5mm exit pupil eyepiece and a filter to help. It's there, but it's tough. That's a tough one.
Yes.
I imaged it and saw basically what's on the screen there, except I disagree with the color scheme a bit. Because I remember to see the bluish or greenish in the central region with a red fringe, and that's also south of.
By the way, I've said this before, and I do want to say it again. We tried to set up an observing program here with the club. We started with the Messier Marathon award system, and Mike and I were driving in today, and I was talking about that. I set the thing up. Bruce made a very nice awards poster. We talked it up, and then nobody came to do it except for myself and Mike. So it's kind of embarrassing to talk up this award, and then you're one of the few that gets to get it. So I was disappointed. We tried to get an observing award program going here. It really didn't fly. I do recommend, if you are that way, you're goal-oriented, and you like to have an incentive to do some observing, check out the Astronomical League. They had a ton of good programs. And I'm very proud of this club for this. We've embraced this whole program. We literally have taken it over. The Las Vegas Club has little to do with it now, and they were going to drop this thing because not much was happening, but this club has picked it up. So I do appreciate any of you that happen to make an observation of this or any of you, just send something into them. You'll find the address in the newsletter, and we'll go from there. We'll go to the next slide and get
I
on.
had a comment I wanted to put in. So you're asking about what it looked like visually. So in the 10-inch, I did see a bit of a cluster there. Specifically, if you look in that picture, if you look just to the left of the brightest star and just to the right, there's two vertical lines kind of staggered. Those are quite clear visually in a 10-inch and on
Oh, yeah.
Yeah, the one there, and then to the right, just to the right, there's another column of stars. Yeah, that column. Those are very
Oh,
those are
like
very yeah, those are very easily visible visually.
It's like a parallelogram.
Yeah, and the 10-inch, I agree, it was very hard to see, and you could tell it's a brighter area of sky if you're just to the side of it, it's darker background. But with the 25-inch, the clubhouse, I could start to see the modeling of the nebula with the UHC filter.
Okay, thank you.
Chris, where was your 10-inch? Was it in?
It was at the clubhouse.
At the clubhouse.
Yeah, we don't do a Sioux French. I think that's it. Is there anything else, though? Oh, Iwamoto. Who's taking that one?
You are. Well,
Oh.
Is Doug here?
Yeah.
All right, Doug. Yeah. Would you like to take it on?
Yeah, well,
Yeah, I'll turn it over to Doug. Keep looking up. Thank you.
it was there. Peak was a couple days in the future, but the weather was predicted to be bad, so I grabbed it while I could. 39 30-second subs. 5.6-inch camera lens, camera sensor. Little, if you can see little gaps in the star trails there, those are my refocus intervals. Other than that,
Well, thank you for the submission. It's great.
sure.
So who can speak to this? How long will we be able to see it? I know it's moving incredibly fast, isn't it? And,
I think the problem is you get the moon getting brighter and brighter as the comet gets fainter, so the window's closing fast.
yes. All right. We have our outreach committee report.
Well, good evening, everybody. Happy Valentine's Day. I just want to go back for a second to the observing stuff. It was mentioned that there's an ISS transit coming up, and about a year ago, Bruce sent a link out to a nice website that gives nice predictions for ISS transits, for lunar and solar transit.
Yeah.
So I'll dig that up and send that out in a discuss email. But what I wanted to say was that as a homework assignment, I think I've offered this before, no one's probably done it yet. So get your homework done. If you've never looked at the ISS through a telescope, you really have to do that. In a pair of binoculars, you can distinguish, 7x50 binoculars, you can distinguish between the core of the space station and the solar panels. In a telescope, not even a big telescope, not even a lot of magnification, you can actually see the solar panels and the modules. Now, you have to track it across the sky, which is probably the most challenging part of it. I would practice first on jets. Find their contrail, run up the contrail, and then practice to see how that telescope moves on jets. And then use a relatively low power eyepiece. If you have a bigger than 10-inch telescope, my recommendation is you put a moon filter on that thing to cut the glare down. And holy cow, you can actually see the space station. It's really pretty cool. So you have to try it.
It's really cool to keep tracking it as long as you can. See if you can watch it enter Earth's shadow and watch it sort of descend through the color range and getting deeper and deeper red. It's almost
I love the
lunar
burnt
eclipse.
orange look of it.
Yeah.
And then I always say to myself, I wish they'd flip the outside lights on, so we can actually see them as they continue along. Well, I'm just a teeny bit.
It's low magnification, right?
30, 40 power,
30, 40, okay.
right? Not much. Anyway, that's my thing about the ISS.
It's transit-finder.com.
Okay.
Yeah.
Well, I'll send it out in an email. I love that website. Thank you.
I'd like to make a book announcement, and our own John has written a manuscript called "Shallow Sky: Imaging the Solar System with the Masters," and we're really excited about this, and I really want to have John come and give us a presentation on what he's found. So do you want to say a word or two?
Sure, just very quickly. Thank you for that. It's a book basically about the history of amateur solar system observing, and it profiles the leading amateurs, starting with Charles Boyer back in the 60s on up through Don Parker, and then to today's modern masters, people like Prisco and Damien Peach and other names certainly we all know, Thierry Legault. And as I say, it profiles these world-class imagers, the techniques they use, what are the passions that motivate them to spend hundreds of thousands of hours producing the unbelievable images that they produce. And it also profiles the contributions that they've made to solar system science over the years. So I hope some of you are interested in it. The book is available in electronic format as an Amazon Kindle book, and also available from Apple Books. And happy to answer any questions after the meeting if anybody has any.
Great, congratulations.
Thank you.
Thank you. And, I believe the last, at least written down, new business is from Mario.
He left out the fact that it's actually for astronomy, but I've been meaning to do this for a long time, and since they set up a webpage for me, I got an extra page for astronomy. But if you want to hear about medical politics and the latest of how the insurance companies and pharmaceutical companies are screwing us, look at the main page, and at the bottom, I'm updating with the latest every, maybe once a week, something worth reading. But that's mostly for physicians. On the other hand, there's a tab, astronomy. If you go down there, there'll be sub-pages and all the messier objects. The first half NGC, second half NGC, SH objects, IC objects, all the way down the line. And it's almost done. I'm still working on it. But
Who took the pictures?
if I put someone else's picture, it's called plagiarism. So yes, I took all the pictures on it. But feel free to download it. Use it as a resource.
Great.
Should I mention the light pollution?
Yeah, sure.
Okay, since we're in this together. So I was in Washington for the past week, and interestingly, Markey is interested in light pollution stuff because of his Green Deal. But Tuesday night, our governor got the AMA Award for Nathan Davis Award for his work on opioids. And it's well deserved. He did a lot of work with that with the Mass Med, but because being from Massachusetts, I was asked to sit with him. And I'm not sure how it happened, but halfway through the dinner, we started talking about light pollution. One of those things. So it turns out he is interested. Never heard of it. Is interested. I told him Bruce Tarr, who happens to be my state senator, is the co-sponsor, and they happen to be buddies because he is the minority chair. And so he's going to talk to Bruce this coming Monday. I'm going to be sending him all the AMA articles I worked on light pollution, and he'll also talk to the speaker. Who knows? We'll see what happens for him.
Great. Mario?
Do headlights on cars.
Actually, yes, because you see, that was never regulated by the Department of Transportation.
It's obviously blue light.
I understand. They let the auto industry self-regulate. But there's been enough complaints that apparently that's changing, and they're going to start trying to eliminate heavy blue lights.
What's the color temperature of those lights? What's the color temperature of those lights?
I don't know. It's not regulated by the government. It's self-regulated by the auto industry.
Okay, thank you very much, Mario. I'm not sure Mario understands that. I work in the pharmaceutical industry. I'm trying to work on curing cancer, so I think there's a good balance, and I'm working.
As long as you have a reasonable rate of return, I love you. But if you're going to charge $1 million for one treatment, we have a problem.
I don't have a problem with that also. So great. Any other new business that we didn't record?
Something, because we often let these things slide until the last minute, something we need to be thinking about. November 11th will be an interesting day. Does anybody know what November 11th, besides being Veterans Day, would be?
Transit of Mercury.
Transit of Mercury. And we're in the entire transit visible area. Granted, November is generally not good for observing, but we should be thinking about it.
Oh, that's great. I'm gonna suggest you drive that one. All right?
Well, I'm going to be driving it for another organization, so I don't know what ATMoB's going to want to do.
Okay, thanks. I'll make a note of that. Great. All right, anything else, any other new business? All right, without further ado, any other questions, comments? I'm going to cut people off pretty much. But thank you.
You were saying that we want people contacting the legislature?
Oh, yeah.
So, just quickly, I passed out little things. Our dark sky bill is out for another round, and we've gotten a lot more politically savvy this time. It turns out one of the things that's really important is having co-sponsors on the bill. There's a House version, a Senate version. Last time I checked, if you live in Massachusetts, you have a House rep and a senator who represent you. Please call them. They're generally quite willing, if a constituent calls, to add their name to a bill that's important to the constituents. So the more people we get, just as a for example, we already have 24 co-sponsors. I've been working with the Mass Municipal Association to get their endorsement. And I said, oh, we have 24 co-sponsors. And they said, wow, that's a lot. That got their attention. So please help in that regard.
That's great. If you go back about a month, I think in Discuss, I put an update on how to reach your senator and your representatives, and just go back into the forum. You can find that information. I can resend it also. So that's great. Thank you. So here we go. I want to take a moment to recognize Camille Carlisle, who offered to come speak to us on Valentine's Day, and I have to admit, she wasn't the first person I called. A couple people said, well, I'm kind of busy and married. I'm like, it's kind of a rough night. But she was great. She offered to give a talk on black holes tonight, and she said, what better night to speak about her favorite love, black holes. So with that, I'd like to turn over the podium to
I come before you tonight as a woman on a mission. A mission to end the disastrous and nefarious smear campaign against black holes. Think about how black holes are normally portrayed. Monsters, beasts, merciless ogres that devour anything within reach. The popular imagination casts black holes as the great destroyers, capitals distinctly enunciated. But is that really a fair depiction? I contend that black holes are no more evil than this beast. This evening I want to challenge any assumptions you may have walked in with about black holes being scary, and take you on a journey through some of the things that we know about black holes. By the end of the talk, I may not have convinced you that these really are the adorable terrors of the cosmos, but at the very least, I hope you will come away convinced that the universe without them would just not be as much fun. So, with that in mind, here's what we're going to discuss. The mic is not working. What do you mean the mic is not working?
Well, it was.
The battery. What? If I just talk loud, is it? Okay.
Yep, that'll work.
Theater voice. If anyone in the back ever has trouble hearing me, just raise your hands and I'll start shouting again. Or more, less, whatever. So, we're going to start with what is a black hole. Now, I'm going to be mixing a little here from theoretical physics and observational astrophysics. And I have to include a caveat that we are not actually 100% sure that the black holes in our theories are actually the same thing as the black holes in the universe. However, I'm going to take what may be a rather bold assumption and conflate them. And I think it is actually a reasonable thing to do because even if they are not exactly the same thing, we have reason to think they're very similar. Then I'm going to go right to the heart of challenging black holes' nasty reputations and give you an example of how they actually create and don't destroy. Then we're going to talk about ways we're trying to see these invisible thingamajigs. And then we're going to spend a couple minutes talking about something very minor, which is the future of all physics. No big deal. So, first things first, what is a black hole? At this early in the talk, I'm under no illusions. Many of you are still struggling potentially with villainous associations. But when it comes to dealing with monsters, the first way to conquer fear is to understand the thing you think is a monster. And in order to understand black holes, we need to start with gravity. And none of this Newtonian nonsense. We are cutting straight to Einstein's theory of general relativity. Now, in GR, gravity is geometry. Space and time form a four-dimensional fabric. And we often talk about them as a rubber sheet stretched top that can warp and curve. And if I were to set an object on this sheet, like so, think of it as a bowling ball, perhaps, it'll warp that sheet. That warp is what we experience as gravity. It's analogous to the way all matter and energy warp space-time. Now, imagine I were to take a ping pong ball and roll it across the sheet. And let's assume, because this is illusion, that I have good aim, and I can roll it straight. Now, if I roll it far from the object, it's going to follow a straight path. But the closer I get to the object, you guys can see the laser pointer, right?
Yes.
Yep. Great. The closer I get to the object, it might bend its path a little. So much so it might bend a lot. This is what light experiences when it shines through the universe, when it's passing around objects. Light photons, as they're traveling along, have to navigate the warped space-time created by matter. And it's kind of like a car, like navigating a mountain pass. It wants to go the shortest distance, but it has to deal with a path that isn't actually straight. Now, let's imagine I put a dinner plate on the sheet. It's going to warp a little, right? Now if I take a paperweight that's the same mass as the dinner plate and put it on the sheet, it'll warp more. It's because the paperweight is more compact, and compactness matters when warping spacetime. A denser object will warp spacetime more than a more spread out object. And this is where black holes come in. Black holes are so compact that they create this inescapable ditch in spacetime. But here's the important thing to understand. The black hole doesn't just create a ditch, it is a ditch. A black hole is a cosmic pothole. It is an object made of warped space-time that's held together by its own gravity. Now, I am not going to take you through the long and torrid history of how black holes became accepted science. If you'd like a synopsis, you can read my master's thesis. It's online through the MIT library, self-promotion moment. But just suffice to say that there are a lot of different lines of evidence that make us think these are real. We can measure the masses of very large, invisible things in the centers of galaxies by clocking the stars and the gas that go around them. And there's millions and billions of suns worth of mass in there, and yet we can't see them. Rather disconcerting. They also explain the glow from active galactic nuclei. We think the gas falling into these ditches is heating up and glowing and potentially powering jets that we see. We also see smaller scale ones like those that are paired up with stars. The classic example is Cygnus X1, where you've got this object that's 50 to 20 times the mass of the sun, and you can't see it, except for the X-ray glow of this gas that's tearing off the neighboring star. And the newest and potentially most compelling, depending on whom you ask, is gravitational waves. We see ripples in the fabric of space-time that look just like we'd expect if the black holes in GR actually exist and are merging. And here's one example. So here's a lovely picture from Hubble. It's galaxies. Now here's the same picture in X-rays. You've got a bunch of flickering dots here. Every dot is a galactic center, powered, we think, by a black hole. And you notice with time that these dots are flicking off and on. It's because black holes are notoriously variable. They're not evil, but they are fickle. And the accretion physics is just not smooth. And so we see this variability. Now, there are two major types of black holes. And I talked about black holes being compact. Not all black holes are equally compact. So you've got the smaller versions, the stellar mass ones. We're talking 5 to roughly 50 solar masses. And these are created by dying stars and supernovae. We find them because they form binary systems with stars, and they're tearing that gas off like a puppy does to cover off an ottoman. And these black holes create steep pits in space-time. They're so steep that the gas falling in heats up so hot it radiates in X-rays. Now, there's the much larger ones, the supermassive ones, which are my personal favorite. They pack millions to billions of suns worth of mass in a space that is about the scale of the inner solar system. Can you imagine there were a million stars within the orbit of Earth? I mean, just think about that for a moment. Now, the creation of these is unclear. There's debate about whether they were big, beefy stars in the early universe that collapsed and formed seeds, or big clouds that just collapsed directly and created these black holes. It is that maybe they exist. They sit at the centers of most large galaxies. The reason I don't say all is because we know that M33, Triangular Galaxy, doesn't have one. And there's no sign of it being kicked out. And we don't know why. And these black holes, though, even though they are larger, their pits are more gently sloped. And so their accretion disks, the gas around them glows primarily invisible and ultraviolet, but we do see X-rays from sort of the haze around that reflecting back off and stuff. So let's look a little bit more carefully at the anatomy of a black hole. Now, you've got this big hot disk of gas, what I like to think of as the tutu. And it is so hot that it creates its own wind and launches gas off itself. Black holes are very sloppy eaters. They eat a small fraction of what's actually on their plate. And they tend to slop it around everywhere. I might remind you of some dogs you know. They also, we think, power, by means of their spins, these plasma jets that for the supermassive black holes can stretch thousands of light years. And if they get enough energy, they can create some mayhem in their environments. And if you've ever been hit by a dog's muscular tail, you might know what that feels like. Now, I'm going to take, in this point, a little more theoretical physics side. Get a little closer. Now, the most famous part of a black hole is the event horizon, the point of no return, right? And that's the distance from the center of the black hole such that you'd have to travel faster than the speed of light. And guess what? That's impossible, so you're going to go in. Hope you brought your helmet. Now, you can think of the black hole as the border or boundary of the black hole. Everything inside the event horizon is the black hole. And your next question undoubtedly is, what's inside a black hole? Thank you, Kevin. I brought my active audience with me. We don't know. I'm sorry. There are some ideas, but physicists do not agree about what is inside a black hole. For the simplest kind of black hole is the non-spinning variety. It's called the Schwarzschild black hole after Karl Schwarzschild, who derived their existence in 1916. And out of the math, we think there's this thing called a singularity at the center. Now, the definition of what a singularity is depends on whom you ask. Some people call it an infinite point of density, some people call it a point in time, some people call it where God divided by zero. The most general, accurate description I can give you is that it's where our understanding of physics breaks down. And things get even more complicated when we go to spinning black holes. Now, singularities come out of the math for non-spinning black holes, but physicists don't agree about what lies down the throat of a spinning black hole. And this is an issue because real black holes spin. We know this because we actually have spin measurements for a couple dozen supermassive black holes at this point. We also have them for some of the stellar mass black holes, maybe about 15 for the ones in binaries. We also have spin measurements for the black holes created in the LIGO mergers. So we've seen 10 black hole mergers with LIGO, and they can determine what the spin of the resulting black hole is based on the shape of that waveform, of that gravitational wave. They all spin. Most of them spin very close to their maximum spin. And so this is really a puzzle because if we don't know what happens in spinning black holes, I can't tell you what's in them. This is your first mental stretch break. I know that some stuff I'm talking about is a little esoteric, and some of you are here under duress, whether because you're my roommates or because you have been dragged here by your loved ones instead of to a romantic dinner on St. Valentine's Day, and if that's you, I'm sorry. This is also my water break. So this is St. Paul's outside the walls. It is outside the walls of ancient Rome. It used to be the papal basilica before St. Peter's was finished in 1615, and if you are ever looking for a gorgeous place to visit that is low on crowds in Rome, I highly recommend St. Paul's.
On the previous slide, there was the word ergosphere.
Oh! I forgot that was in there. The ergosphere is the term for the region that is twisted by the black hole spin. So as a black hole rotates, it drags space-time around with it. All right. So far I haven't done much to convince you that black holes are not insatiable cosmic death traps. So let's talk about how narrow, small their reach actually is. And we'll take the big black hole at the center of the Milky Way as an example. It's called Sagittarius A star. It's 4 million solar masses. It's about 26,000 light years away, but its gravitational reach is only about 10 light years. And it only dominates the motion of stars and gas nearby within about 1/3 of a light year. That's on the order of the size of the Oort cloud. Much, much smaller than the galaxy. We're safe. People sometimes ask me this at parties, they're like, are we falling into the black hole at the center of the Milky Way? I'm like, no, you're fine. Don't worry about it. But stars, have no problem existing much closer than that to the black hole. Particularly, if you've been reading things I'm writing, I'm sorry, you're getting a review. The S stars. We know about 36 of these big, bright, they're B-type stars. Within about, the farthest they get from the black hole is about 8,000 astronomical units, about 8,000 times their sun distance. And they're all a few million years old. And this is troubling, because stars should not form here. The black hole's tidal gravity should shred the gas clouds that make stars. And in order for them to have migrated here from somewhere else, they need a whole lot more than a few million years. This is really baffling to astronomers that these stars exist. But there they are. So what are you going to do? You're going to come up with ideas. And there are two main theories for how these stars got here. One of them is what I call the slingshot method. So you've got this binary star, it's minding its own business, and then it interacts with a gas cloud that wasn't minding its own business, and it slingshots the binary at the black hole. Now when the binary gets close to the black hole tears the binary apart, keeps one star for itself, it flings the other one out at high speeds such that it can actually go out of the galaxy. And we have actually seen about a dozen of these rejected stars, and they're the same spectral types as the S stars. The, to me, more exciting possibility, and one that cuts right to what I want to do tonight about undermining black holes and astro rotations, is that the black hole actually created these stars. Now, say instead of you having a binary and shooting at the black hole, you've got a binary in orbit around the black hole. And when you've got this, the black hole plays havoc with the stars' orbits around each other. And it starts to elongate them with time, so much so that their closest approaches to each other get closer and closer until the stars actually merge. And we do have observational evidence of stars merging, so this isn't just a pie-in-the-sky idea. Now, when stars merge, it creates a new, more massive star, and it resets the star's clock. This is very good, because the S stars then could have been created by, say, billion-year-old stars, And those stars would have had time to migrate this close to the black hole and then merge. The second part of why this is exciting is that for about 1 million years, this new made star will have this sort of red, dusty envelope around it of gas. And astronomers have actually seen several objects that look just like that in the galactic center. Currently, I think the numbered official ones are 5, or G-type objects. And I've never really gotten a straight answer about what G stands for and what S stands for, but I think G is for gas, because they look gassy. And these, most of the G-type objects are on pretty elongated orbits around the black hole. And that kind of orbit around the black hole, if a binary star was in that orbit, it would merge faster. This is your second stretch break, my second water break. I drink a lot of water, guys. This is my life in a cartoon.
So, may I ask a question about what you mean by resetting
the stellar clock? Yes.
The stars on their own are gradually becoming hydrogen depleted in their cores, but by merging, they rehomogenize and they become homogeneous.
Yeah, and you've got. I'm not sure exactly how the core fractions break down, but yeah, everything mixes up a lot. And because the cores are going to merge, and there's all this stuff getting sloughed around, and so yeah.
Does the medicine change of the stars? Like, then we can see the stuff that was in the core becomes.
I don't know. And they're still trying to figure out what the observational imprints of this would be, so that they could look at the S stars, and they haven't come up with a list yet. They're still simulating, I think. All right, so far I've talked a little bit about what we think a black hole is, some of the effects they have. The kicker is we haven't actually seen one. Now, that may not bother some of us, but it does bother astronomers. And so, how do you go about seeing something that is quote-unquote invisible? Well, you don't see the black hole itself, but you can see its silhouette.
You mean perceive or see?
I meant see.
But perceive them would imply that you don't necessarily, for example, an explosion, you don't need to see to perceive.
True. But we should be able to perceive the silhouette and see it in images. So then I can do both. So, I mentioned earlier that black holes warp the path of light around themselves. Now, if you've got a black hole with an accretion disk, I'm sorry, Mario, you're about to see through me. If you've got a black hole, you've got the accretion disk around it. The light from the disk on this side of you is fighting the black hole's gravity to escape. And so some of it's going to fall in. You've got this darkness here. Then you've got the light from the accretion disk behind it. And the black hole's gravity is so strong that it warps and lenses and magnifies the light from the top of the disk around. And the same thing happens with the bottom of the disk. It gets warped around. And then you've got the disk coming in right here, faint here. The whole thing creates a silhouette. And what's particularly important is the circular ring right around the event horizon. That is called the photon ring. And that is a very specific prediction of general relativity. And GR actually tells us what the size of that should be. It's about 5 times the event horizon. Now, for the black hole at the center of our galaxy, given how far away it is, that would be about 50 micro arcseconds, which is like looking at an orange on the moon. You need a really big telescope. You guys know that. You need a planet-sized telescope, which is why astronomers are putting together the Event Horizon Telescope Project. This is organized primarily by Chef Dolman, but they've been basically pulling in every black hole astronomer there is at this point. It's really hard to find someone to interview who's outside of the project at this point. 10 years ago, that wasn't a problem. The Event Horizon Telescope is a global network of radio telescopes. And they work by process of interferometry. They combine their observations such that they create a planet-sized telescope. But even though they observe simultaneously, this is seen as from the source's perspective, so the black hole looking at Earth, the observations don't combine simultaneously. They actually have to timestamp all the observations with precise atomic clocks, put that on hard drives, ship them back here to Boston, and combine the observations. They call it astronomy with FedEx. And when they do this, they should actually be able to reconstruct in, sweeping form, or in not really high detail form, the image of that silhouette. They may actually even be able to do movies. They're talking about this now. There's some debate amongst people on the EHT how successful this might be. But some of them are very convinced. And the ones who are very convinced, I believe them. And what that would do is you could actually watch how the accretion flow changes, how the brightening and everything changes over time. Now it's going to be hard with Sag A star because the black hole varies on about the scale of 30 minutes. And there's going to be a lot of smearing there in the image if you're averaging observations across a globe. Probably would be much easier with M87. That black hole is much larger, and the variability is on the scale of years. So we may actually be able to construct videos of how the light around the silhouette changes with time. Now, interestingly, if we go back here, this simulation is done assuming you're looking pretty edge on with the disk. There are a couple of observations that were announced in the last few months that suggest we're not actually looking straight on at the disk. We may be looking straight down, like the black hole's forehead. The first of these came out of the gravity collaboration. They hooked up the 4 8-meter telescopes at the Very Long Telescope Interferometer in Chile, and that's in near infrared. And they were able to see 3 distinct flares near Sagittarius A star. And the flares didn't stay in place, looped around the black hole. And they went fast. We're talking 30% the speed of light, and they took 45 minutes to go around the black hole. They were not slowing down. And this behavior looks just like what you'd expect from a hotspot, which they don't actually entirely understand what a hotspot is created by, but they're going with the term hotspot in the disk. But you wouldn't see it make this loop unless you're looking down at the disk as it's going around, right? You wouldn't see that from the side. So there's one point in favor of looking down the disk. The second one came right after that. It was part of support observations with the EHT. And they were trying to figure out how to tease out the effect, the scattering effect of the interstellar medium, the clumpy clouds between us and the black hole. And they were able to reconstruct what looked like a pretty uniform circle of emission from the black hole, which you'd only get if you're looking straight down at the disk or down the barrel of a jet. And we don't know if our black hole has a jet or not. There's been a lot of attempt to figure it out, but we have nothing definitive whether we've got a jet. So, but we can only do the Event Horizon Telescope for a handful of supermassive black holes. So how are we going to look at the rest of them? Well, gravitational waves are, in many ways, the name of the game. We won't be able to do it with LIGO. LIGO is stellar mass black holes, but we're going to need Europe's LISA spacecraft that should hopefully launch in 2034 to detect mergers from supermassive black holes. And gravitational waves are great. But we're astronomers. We want light effects, right? And so astronomers have been trying to figure out, well, could we see anything? Could we detect any radiation from these mergers? Now, the stellar mass black holes, by the time they get to merger, they've cleared out all the gas around them. So there's no light to be seen. Not true for supermassive black holes. They will both still each have a disk of gas around them, and I'll show you a simulation of this in a moment. They will also have a circumbinary disk, a big disk around the pair. And the gas is not staying still. The gas is sloshing back and forth between the two mini disks. Their filaments peeling off and slamming into one. hitting the other ones, it should all create light effects. And so what they did is they put together simulations of what this might look like. And they're not at the stage yet where they can say, observers, look for this. This is what we'd see from a binary. We're just starting baby steps toward that. Most of the simulations are just really cool to watch. And so I'm going to show that to you. I think that's all I have to say about it. So let's see if it plays. Yes, it's pretty. Whee! So this is a simulation of 2 supermassive black holes done by Manuela Campanelli's group at RIT. And you've got the 2 mini disks. This one, and the circumbinary disk. It's going to light up each of these in a second. There we go. That's the circumbinary disk. You have the mini disks. The accretion flows from one to the other. And then unfortunately, because it was too computationally expensive, they didn't show where it's sloshing back and forth. It's sat in this box. The purple is ultraviolet, and the blue is X-rays. Now this gas is heated by magnetic and gravitational forces. And so as everything's sloshing around, they determined that you're going to see ultraviolet from basically all parts of that. X-rays primarily, as you saw in this. Now, if we change our viewing angle, we get to see a wild show. This is where you really see how light has to travel through the warped space-time that black holes create. And it's going to create these bizarre effects, right? You've got this lensing as one black hole passes in front of another. And, right? Talk, just watch it. Then we zoom in, whee! Wow. And then there's this thing they like to call the eyebrow, which may have been because they needed a press release term, but they're calling it an eyebrow. And then you see it from a different angle, whee! And then you can see both silhouettes at the same time. Now, no foreseeable technology is going to permit us to see it this way, but if we can figure out what exactly those light effects might be, we could look for those in distant galactic nuclei. It's just pretty. And this is by NASA Goddard. Thank you, Brett. All right. Now the next mental stretch break may make more sense to the ladies in the room. Ladies, you know when you say to a woman, I love your dress, what's the one way that she can up the ante? It has pockets. This is why the black holes make the universe more awesome. Because they're like pockets. See, I told you the girls get this. All right. So, why do we want to look at a black hole? It's not just because it's there, although that's enough for some of us. The Event Horizon Telescope sprouted from physicists' belief that black holes really are the key to the next generation, next revolution in physics. Physicists want a quantum theory of gravity, a master framework that unites general relativity with quantum mechanics, the physics of the very big, but the physics of the very small. And a lot of people, I think, when they hear this, if they heard this term, they think it's some sort of esoteric goal. It's not. And to prove to you, I want to see a show of hands. I want audience participation here. Put your hand up if you've ever used GPS. Google Maps. Not generally? Yeah. Keep them up. Keep them up. You've all used general relativity. Okay, you can put it down now. Remember at the beginning I said that gravity is the warping of space-time. Not just space, space-time. A clock on the surface of the Earth ticks more slowly than a clock on a GPS satellite. I think the difference is about 38 microseconds per day. It builds up. And if we did not account for the effects of the warping of space-time, we would have no GPS system. Welcome to modern physics. Now imagine if we were able to merge GR with quantum, how our everyday lives might change. Now, I have to be careful in this section of the talk, because I'm doing something you should never do in a talk. which is talking about something at the fringe of my understanding. And so I may not actually be able to answer any questions in this section. I'm warning you in advance. But I'm taking the risk because I firmly believe, and many physicists firmly believe, that black holes really are going to be the way we break open quantum gravity. And I want you to at least have heard of these ideas before, hopefully at some point, they become mainstream. So, thanks to decades of grappling with black holes, physicists are piecing together a working theory of quantum gravity. We do actually have a working theory of quantum gravity. There's one big catch. It only works in a universe with a geometry opposite to our own. Now don't let this alarm you. This is a common tactic among theorists. You work it out in a space that's friendlier, and then you move it to the real universe. But this quantum gravity theory arose after we realized, thanks to looking at black holes, that the amount of information you can stuff in a black hole is proportional to its surface area. Now it's fine. This is somewhat related to why Stephen Hawking is so famous, actually. And so, what the quantum gravity framework of discovery inspired is often called a soup can model, where you've got everything in what's called the bulk, the contents of the can, that is our higher dimensional gravity-infused universe. And everything in that can is described by what's on the label, which is a lower dimensional quantum framework. And what the theorists found is that they can actually do the math in the simpler label situation, and it will describe what's in the bulk. Now, and it's the reason this is called the holographic principle is because it kind of sounds like a hologram. You've got a two-dimensional thing that seems to project a three-dimensional image. Now, to be clear, this does not mean the universe is a hologram. We are not all projections from a distant cosmic label. But the insights from this process, hopefully, will tell us how gravity, space-time, the whole observable universe somehow emerge from quantum effects. And these advances, they're still happening, they're still being argued about, they're still being figured out. They're coming thanks to black holes. Black holes are how we are cracking open physics. And the closer we come to black holes, whether it's through the Event Horizon Telescope or gravitational waves or the stars that we see looping their way around the black hole, this is how we are going to push at the frontiers of physics. So black holes were really part of this big discovery in the 20th century that shook up our ideas of gravity. In the 21st century, black holes are going to be what shakes up physics. So, although you may not believe that black holes are cute, maybe, I wish you did, I do. I hope that at the end of this you do see them as potholes, that they can actually make stars, that they can cast shadows and ripple space-time, and that they may next be the next revolution in physics.
Quantum gravity be a different term than grand unified theory, that is uniting these forces?
Grand unified theory, yeah, that's for the early universe when all the energies, everything was...
No, more bringing the different fundamental forces together, gravity, electromagnetism, and strong nuclear forces. If I understand correctly, I don't. That they haven't been able to bring gravity into
Correct.
that framework.
That is correct. Yeah, so this is really focusing on the quantum gravity is just focused on the quantum and the gravity aspect, and it's trying to understand. Basically, in GR, you've got space-time is this continuous fabric. And when you zoom way down to the quantum, you've got the, it's quantized. It's little pieces. Space-time is not continuous, and they want to figure out how to go from very big to very small without hitting major mathematical props. And so that's what quantum gravity is about. It's not about integrating EM and everything else.
What's the deal with the quantum information paradox?
Yeah, so the quantum information paradox is that if you talk about GR, we talk about an event horizon. Nothing should be able to escape the event horizon. Now, Hawking made a whole lot of quantum physicists unhappy, particularly Leonard Susskind, who wrote a wonderful book called Black Hole War. I recommend it for a more in-depth answer to your question. And basically he said, well, when the Hawking radiation comes out, it won't preserve any information about what went in. That is, the Hawking radiation will always look the same no matter what you threw in there, no matter what the history of the black hole was. And the quantum physicists are like, what do you mean information is destroyed? I think they actually reacted just like that. And so that's the quantum information paradox. It is probably resolved by what's called black hole complementarity, which is different observers see different things. It's kind of like the light can be both a particle and a wave. A black hole can either kill you with a firewall, or you can pass through without no problem. You can pass through if you're the one passing through. You think you'll be fine. I don't pretend that this makes sense. But
what is the firewall?
Yeah, the firewall is almost completely disproven now. There's one holdout. It was part of this trying to reconcile the quantum information paradox. When they were doing the math, they discovered there should be a sheet of radiation if we're doing this right, and most people think they've solved that by now, and they've gotten rid of the firewall.
Yeah, I have a quick question. So we've known about these S stars at the center of the galaxy since, what, the 90s? We've
Late
seen
90s.
them kind of like floating around
Yeah.
in their extreme behavior. And you mentioned that we've got evidence for the binary model where they come in as a set and one of them gets rejected while the other somehow maintains this extraordinary angular momentum or whatever. Do we have much evidence for the other proposition where you've got these mergers? Do we have other ancient stars kind of floating around waiting to be rejuvenated by a companion on a trajectory?
You mean in the galactic center?
Well, yeah. So you've got a dozen or so young stars. We have 24 seniors ready to
So
mate.
we are not yet at the detection capability to see the lower mass older stars. These are the brightest stars. These are B-type stars. So it's really hard, it's really crowded in the galactic center. It looks like a polka dot fabric on steroids when you look at these star images. And so these are the ones they can detect now. They're working on detecting the red giants, the other stars, but it's going to take
So there's enough activity there that there's a probability that there's enough stars?
Yeah.
Yeah.
Yeah, there should be a lot of stars in the galactic center, and we're only probably detecting the brightest ones. And even then, it's just stars everywhere when you look at it.
Is Gaia data going to be useful for
I don't know if Gaia... I honestly don't know if it's going to be able to say much about the galactic center.
It's too small an aperture.
It's too small an aperture, Mario tells me.
Mario
Go
would
with
know.
Mario would know. Yeah.
My type
Yeah.
aperture.
So, I see a hand in the back.
I have a question about the orientation. You mentioned that there's evidence now that we are looking down on the accretion disk of Sagittarius A star. But how can we are on the galactic plane? So how can the disk, the accretion disk of Sagittarius A star, is not aligned with the galactic disk?
This is weird. This is a good question. And so, no, it doesn't. Potentially, there's actually no reason the black hole's accretion disk has to align with the galactic plane, because the black hole has grown over time. It may have grown by mergers, although it would have to be at least 10 billion years ago. There's no evidence of last 9 billion years. But it could have gotten its axis skewed, or the gas coming in. But it does not have to align with the galactic plane, because they're pretty separate. I mean, the galaxy just shoves gas down into the center, and it doesn't have to line up, oddly.
You use the words detect and see and things like that. And it always seems to me that when we talk about anything in physics, it has to have some way of being, I'll go back to my earlier thing about being perceived. Now, earlier on in the talk, you said that we really can't see them, in a sense, because you can't get light out of them somehow. And there has to be something coming out, or you're not perceiving it, you're, I guess you're going to say detecting it because of its effect. And I guess I was left, and so now I'm asking the question, do you expect to perceive it, see it, or know it's there by some other means? And if so, what other means?
So let me clarify, what do you mean by perceive?
Well, when I say perceived, I know it's there because it's had an effect somehow. Something has come to me, and therefore there has to be something there. Even if I don't know what the thing is, I still have to see some effect of it for me to say there is something there.
And how do you distinguish that from detect?
Well, detect, in my mind, in general, means that I'm actually seeing it. But there's not too much difference. Perceive and detect, I'm asking the question because I'm having a problem, because it seemed to me, and maybe I misread the early part of the talk, when you said we're not going to see them, or we don't maybe see them, or light can't escape out of it, or no radiation can escape out of it, and maybe we're going to see light bent or something else. And when I asked the question originally, I can say a difference between see and perceive. Perceive and detect, I'm not so sure there's that much difference, so I'd go for either one of them. But the difference between see, well, I guess there's see, hear, smell, taste, what are the things that we can do? Okay, and then there are things that we sort of know they're there because there are other things happening and have to be there. What the original thing when we went looking for Uranus and Neptune and stuff, we didn't know they were there. We didn't really quite know what the hell they were either, but we knew that there was something that had to be there. That's detecting or perceiving, but without seeing. And I guess
but we detected it by seeing it.
Yes, but we sort of knew it was there. We perceived that it was there.
See, I wouldn't use perceive in that context. I would say we predicted.
I'm willing to let you have your word. Okay? Because you kind of glossed over it, and maybe that's all you can do with it at the moment. I'm not complaining because of the way you approached it. I'm just trying to, in my own mind, if somebody says to me, what the hell did, I want to be able to say something about it.
So, I would say you can't see a black hole in that the black hole does not emit radiation. And I realize some people are really thinking Hawking radiation, but any astrophysical black hole is going to probably have gas around it. It has hot gas unless it's marauding through the universe and visible. But anything with accreting, that accretion glow is going to swamp out the Hawking radiation. We're very likely not going to detect Hawking radiation. So, in short, you're not going to see the event horizon like receiving radiation from it to your eye, kind of thing. We're going to detect that there's a black hole is there through other means.
That's fine.
Okay. Yeah.
What about black holes and wormholes?
So,
We were waiting for that one.
I was. Sounds like I planted it. So wormholes are theoretically possible. They are not known to be able to be stable in the presence of matter, which means you're not going through. There's also very interesting work by Juan Maldacena at, I'm never going to get the institute's name right, Institute for Advanced Studies. It's like right next to Princeton. And his collaborators that suggest, you remember how I said that the warping of space-time? If you go into this throat, time is slower. And it would actually take you longer to pass through a wormhole from point A to point B than just going straight through space, because time moves so much more slowly through that wormhole than it does in regular space. So you don't actually want to take a wormhole anywhere. Sorry, the science fiction has turned on its head. Yes, my esteemed collaborator.
Back to stellar mass black holes for a second.
Yeah.
The ones that merge gravitationally are of order a couple of dozen stellar masses. how do stellar mass black holes get to be that size? Are they from massive stars?
Yes.
Or could they be from mergers of smaller black holes?
So, what's interesting about the 10 black holes that were created in these mergers is that there was a prediction that is now holding up that a black hole that is created by two black holes merging spins about 70% of its maximum allowed spin for that particular black hole. Now, we've got good spin measurements for the ones that were created.
Do you mean ones that LIGO has created?
Ones that the LIGO has detected being created, yes, thank you. And we don't have as clear indications of the spins of the black holes that came before, the progenitors, but they look low. And that would indicate, if they're not all 70, then they were made from stars and they're not second generation black holes. Yes, my esteemed roommate.
A question I think would be relevant and interesting maybe for this crowd is, so LIGO's been exciting because we can do multi-messenger astronomy. So you get the gravitational wave and you look at the X-ray, the radiation, et cetera. So what is, can you talk a little bit about the optical counterpart of these mergers?
The stellar ones or the supermassive ones?
The stellar. Because they're the ones we see followed up.
They're bright and they're cool. Talk about in...
Because there's so in some of these mergers, there's multiple stages of they emit in different wavelengths. And so,
for the neutron star mergers, yeah. The neutron star ones, yes, we're going to see light effects as we did with the one that happened right around the eclipse because it has no respect for astronomers' vacations. The poor LIGO team, they were off trying to see the eclipse and suddenly they get alerts saying, there's a neutron star merger! They were not happy. I mean, they were happy, but they were their families weren't happy. But the black holes, stellar mass black holes when they merge will not have light effects. Almost certainly. They should have cleared out the gas long before they get that close to one another, and so we don't expect any optical. Yes, I see a hand.
Well, I didn't want to take one. I just, after reading numerous books on it, I still don't quite understand what is spinning in the spin.
Great question.
Is it space-time that
Yes.
we're talking about?
We're talking about space-time. So the black hole itself is rotating. But if you think if you take a napkin, you spread it out, and you put your hands on it and you twist it, the napkin twists and tightens around it. That's what space-time does. It's called the lens-Thurian effect.
Okay, but what is creating that?
What is creating this? It's the black hole itself that's rotating.
Okay, so how does it, this is what I'm having trouble with. Is it still a singularity, and how does a singularity cause it?
So we don't know if there's a singularity down the throat of the spinning black hole. There's an event horizon, depending on which physicist you asked, but whatever the heck this ditch is, as it spins, it's twisting space-time. It's the whole pothole that spins, not just, there may not.
Still having trouble with that, but that's okay.
It's okay. It's a weird idea.
I'm gonna, just to be respectful of time and our guest, ask that we have one more question. Make it a good one.
Make it easy. Good, Tony.
So is there any reason whatsoever to believe that black holes smaller than stars exist in real life?
Isn't the LHC supposed to create them?
Well, I mean, that's possible, right?
No, they actually just proved that as part of the science community.
Yes.
Because people were worried. They were, actually. There was discussion about whether there could be primordial black holes that were really tiny.
No evidence.
No, there's not.
Okay.
But
Well,
I don't know.
Yeah.
Yeah, no, sorry.
All right, well, thank you very much. Really wonderful presentation. I want to thank you again and everyone for coming tonight at the risk of your partners' wrath. But I also want to thank Eileen Myers for bringing refreshments tonight, so make sure you reach out to her and thank her specifically and everyone else that makes this such a great event. So Thank you, really appreciate it. Have a great night.